So far we've seen the power of just using a simple multi-layer perceptron to solve a wide variety of problems, but you can take things up a notch. You can arrange more complicated neural networks together and do more complicated problems with them. So let's start by talking about convolutional neural networks, or CNNs for short. Usually you hear about CNNs in the context of image analysis, and their whole point is to find things in your data that might not be exactly where you expect it to be. So technically we call this feature location invariant. That means that if you're looking for some pattern or some feature in your data, but you don't know where exactly it might be in your data, a CNN can scan your data and find those patterns for you wherever they might be. So for example, in this picture here, that stop sign could be anywhere in the image, and a CNN is able to find that stop sign no matter where it might be. Now, it's not just limited to image analysis. It can also be used for any sort of problem where you don't know where the features you are might be located within your data. And machine translation or natural language processing tasks come to mind for that. You don't necessarily know where the noun or the verb or a phrase that you care about might be in some paragraph or sentence that you're analyzing, but a CNN can find it and pick it out for you. Sentiment analysis is another application of CNNs. You might not know exactly where a phrase might be that indicates some happy sentiment or some frustrated sentiment or whatever you might be looking for, but a CNN can scan your data and pluck it out. And you'll see that the idea behind it isn't really as complicated as it sounds. This is another example of using fancy words to make things sound more complicated than they really are. So how do they work? Well, CNNs, convolutional neural networks, are inspired by the biology of your visual cortex. It takes cues from how your brain actually processes images from your retina, and it's pretty cool. And it's also another example of interesting emergent behavior. So the way your eyes work is that individual groups of neurons service a specific part of your field of vision. So we call these local receptive fields. They are just groups of neurons that respond only to a part of what your eyes see. It subsamples the image coming in from your retinas and just has specialized groups of neurons for processing specific parts of the field of view that you see with your eyes. Now these little areas overlap each other to cover your entire visual field, and this is called convolution. Convolution is just a fancy word of saying I'm going to break up this data into little chunks and process those chunks individually. And then they'll assemble a bigger picture of what you're seeing higher up in the chain. So the way it works within your brain is that you have many layers. It is a deep neural network that identifies various complexities of features, if you will. So the first layer that you go into from your convolutional neural network inside your head might just identify horizontal lines or lines at different angles or, specific kinds of edges. We call these filters. And that might feed into a layer above them that would then assemble those lines that it identified at the lower level into shapes. And maybe there's a layer above that that would be able to recognize objects based on the patterns of shapes that you see. And then if you're dealing with color images, we have to multiply everything by 3 because you actually have specialized cells within your retina for detecting red, green, and blue light. And we need to assemble those together as well. Those each get processed individually too. So that's all a CNN is. It is just taking a source image or source data of any sort really, breaking it up into little chunks called convolutions, and then we assemble those and look for patterns at increasingly higher complexities at higher levels in your neural network. So how does your brain know that you're looking at a stop sign there? Let's talk about this in more colloquial language, if you will. So like we said, you have individual local receptive fields that are responsible for processing specific parts of what you see. And those local receptive fields are scanning your image and they overlap with each other, looking for edges. You might notice that your brain is very sensitive to contrast and edges that it sees in the world. Those tend to catch your attention, right? That's why the letters on this slide catch your attention, because there's high contrast between the letters and the white background behind them. So at a very low level, you're picking up the edges of that stop sign and the edges of the letters on the stop sign. Now a higher level might take those edges and recognize the shape of that stop sign. It says, oh, there's an octagon there. That means something special to me. Or those letters form the word stop. That means something special to me too. And ultimately that will get matched against whatever classification pattern your brain has of a stop sign. So no matter which receptive field picked up that stop sign, at some layer it will be recognized as a stop sign. And furthermore, because you're processing data in color, it can also use the information that this stop sign is red and further use that to aid in its classification of what this object really is. So somewhere in your head there's a neural network that says, hey, if I see edges arranged in an octagon pattern that has a lot of red in it and says stop in the middle, that means I should probably hit the brakes on my car. And at some even higher level, where your brain is actually doing higher reasoning, That's what happened. There's a wire that says, hey, there's a stop sign coming up here. I better hit the brakes in my car. And if you've been driving long enough, you don't even really think about it anymore, do you? Like, it's almost hardwired, and that literally may be the case. Anyway, a convolutional neural network, an artificial convolutional neural network, works the same way, same exact idea. So how do you build a CNN with Keras? Obviously, you probably don't want to do this at the low-level TensorFlow layer. You can, but CNNs get pretty complicated. A higher-level library like Keras becomes essential. First of all, you need to make sure your source data is of the appropriate dimensions, of the appropriate shape, if you will. And you are going to be preserving the actual 2D structure of an image if you're dealing with image data here. So the shape of your data might be the width times the length times the number of color channels. And by color channels, I mean, if it's a black and white image, there's only one color, black and white. So you'd only have one color channel for a grayscale image. But if it's a color image, you'd have 3 color channels, one for red, one for green, and one for blue, because you can create any color by combining red, green, and blue together. Okay. Now, there are some specialized types of layers in Keras that you use when you're dealing with convolutional neural networks. For example, there's the conv2D layer type that does the actual convolution on a 2D image. And again, convolution is just breaking up that image into little subfields that overlap each other for individual processing. There's also a conv1D and a conv3D layer available as well. You don't have to use CNNs with images. Like we said, it can also be used with text data, for example. That might be an example of one-dimensional data. And there's also a conv3D layer is available as well if you're dealing with 3D volumetric data of some sort. So a lot of possibilities there. Another specialized layer in Keras for CNNs is max pooling 2D. Obviously, there's a 1D and 3D variant of that as well. The idea of that is just to reduce the size of your data down. So if I take just the maximum value seen in a given block of an image and reduce the 2-layer down to those maximum values, it's just a way of shrinking the images in such a way that it can reduce the processing load on the CNN. As you'll see, processing CNNs is very computing intensive, and the more you can do to reduce the work you have to do, the better. So if you have more data in your image than you need, a max pooling 2D layer can be useful for distilling that down to the bare essence of what you need to analyze. Finally, at some point, you need to feed this data into a flat layer of neurons, right? At some point, it's just going to go into a perceptron. And at this stage, we need to flatten that 2D layer into a 1D layer so we can just pass it into a layer of neurons. And from that point, it just looks like any other multi-level perceptron. So the magic of CNNs really happens at a lower level. Ultimately, it gets converted into what looks like the same types of multi-layer perceptrons that we've been using before. The magic happens in actually processing your data, convolving it, and reducing it down to something that's manageable. So typical usage of image processing with a CNN would look like this. You might start with a conv2D layer that does the actual convolution of your image data. You might follow that up with a max pooling 2D layer on top of that distills that image down, just shrinks the amount of data that you have to deal with. You might then do a dropout layer on top of that, which just prevents overfitting like we talked about before. And at that point, you might apply a flatten layer to actually be able to feed that data into a perceptron, and that's where a dense layer might come into play. So a dense layer in Keras is just a perceptron, really. It's a hidden layer of neurons. From there, you might do another dropout pass to further prevent overfitting, and finally do a softmax to choose the final classification that comes out of your neural network. Now, like I said, CNNs are compute intensive. They are very heavy on your CPU, your GPU, and your memory requirements. Shuffling all that data around and convolving it adds up really, really fast. And beyond that, there's a lot of what we call hyperparameters, a lot of different knobs and dials that you can adjust on CNNs. So in addition to the usual stuff you can tune, like the topology of your neural network, or what optimizer you use, or what loss function you use, or what activation function you use, there's also choices to make about the kernel sizes. What is the area that you actually convolve across? How many layers do you have? How many units do you have? How much pooling do you do when you're reducing the image down? There's a lot of variance here. There's almost an infinite amount of possibilities here for configuring a CNN. And often just obtaining the data to train your CNN with is the hardest part. So for example, if you own a Tesla, that's actually taking pictures of the world around you and the road around you and all the street signs and traffic lights as you drive. And every night it sends all those images back to some data server somewhere so Tesla can actually run training on its own neural networks based on that data. So if you slam on the brakes while you're driving a Tesla, at night, that information is going to be fed into a big data center somewhere, and Tesla's going to crunch on that and say, hey, is there a pattern here to be learned of what I saw from the cameras from the car that means you should slam on the brakes in the case of a self-driving car? And if you think about the scope of that problem, just the sheer magnitude of processing and obtaining and analyzing all of that data, that becomes very challenging in and of itself. Now, fortunately, the problem of tuning the parameters doesn't have to be as hard as I described it to be. There are specialized architectures of convolutional neural networks that do some of that work for you. So a lot of research goes into trying to find the optimal topologies and parameters for a CNN for a given type of problem. And you can just think of this as like a library you can draw from. So, for example, there's the Linnet 5 architecture that you can use that's suitable for handwriting recognition in particular. There's also one called AlexNet, which is appropriate for image classification. It's a deeper neural network than Linnet. So in the example we talked about on the previous slides, we only had a single hidden layer, but you can have as many as you want, really. It's just a matter of how much computational power you have available. There's also something called Google Linnet. You can probably guess who came up with that. It's even deeper, but it has better performance because it introduces this concept called inception modules. They basically group convolution layers together, and that's a useful optimization for how it all works. Finally, the most sophisticated one today is called ResNet. That stands for residual network. It's an even deeper neural network, but it maintains performance by what's called skip connections. So it has special connections between the layers of the perceptron to further accelerate things. So it sort of like builds upon the fundamental architecture of a neural network to optimize its performance. And as you'll see, CNNs can be very demanding on performance. So with that, let's give it a shot. Let's actually use a CNN and see if we can do a better job at image classification than we've done before using one.